Hello friends, today we'll solve the control system problems of grade 2024 electronics and communication paper. So this is the first question. It is saying that in the context of body magnitude plot 40 dB per decade is same as. So we need to convert it into octave. Okay. So here you should know that plus minus 20 n times dB per decade is plus minus 6 n dB per octave. Okay. So here it is 40 dB per decade, so it will be 12 dB per octave. Okay. You can also remember it like 1 dB per decade is 0.301 dB per octave. So what does that mean? It means that if the frequency changes by 10 times, then we say a decade times. Decade means a 10x change, 10 times change in frequency. For example, 10 hertz to 100 hertz. So the frequency changes from 10 to 100 and then 100 to 1000, then we say it is 20 dB change, because first 10 dB then again 10 dB, so 100 to 1000 hertz means 20 dB. Okay, like that. So 10 to 100 hertz is 10 dB. Then the magnitude changes by 20 decibel, which is as good as if the frequency changes by 2 times, which is called as octave. Then the magnitude changes by 6 decibels. Okay, so 20 dB per decade is 6 dB per octave, so 40 dB per decade is 12 dB per octave. Decade means a 10x change in frequency and octave means 2x change in frequency. Okay. Second question is on steady state error. It is saying that in the feedback control system shown in the figure below, given GS as 6 upon S plus 1, S plus 2. So this is GS. Now RS, YS and ES are the Laplace of RT, YT, ET respectively. So if the input RT is a unit step function, then we need to find basically which of the following is correct, which is limit t tending to infinity et. So basically it is asking about the value of steady state error. Okay. So here three options look normal, but fourth option is saying that limit t tending to et does not exist because et is oscillatory. So whenever such option is there, then first we need to find the characteristic equation and check whether the system is stable or not, because if the system is unstable or oscillatory, then this steady state error value cannot be found. Okay. So ESS can only be calculated for a stable system and never for marginally stable or unstable system. Okay. So first we need to find the characteristic equation and find a comment on the stability of the system. Okay. So since it's a unity feedback system, so characteristic equation is 1 plus GHHS. So 1 plus this is GS. GS is what? This is 6 upon S times S square plus 3S plus 2. So this is S cube plus 3S square plus 2S. This thing. So this is 1 plus this 6 upon S cube plus 3S square plus 2S. Okay. This thing equal to 0. Then this becomes S cube plus 3S plus 2S, and this becomes S cube plus 3S plus 2x plus 6 equal to 0. So this thing goes there. So characteristic equation is S cube plus 3S square plus 2S plus 6 equal to 0. Now you can see that all the signs are same, and this internal product is 6, external product is also 6. So whenever internal coefficient product is equal to external coefficient product and all signs are positive, then we can directly say that the closed loop system is marginally stable. Okay. And since steady state error can only be calculated for stable system, so steady state error does not exist, cannot be defined for this given closed loop system. Or we can say that ET is oscillatory error, ET will be oscillatory in nature. Okay, so limit t tending to infinity ET does not exist, so correct answer would be D. Okay, so directly we should not apply that table and use KV and KN, KP values, because that is a trap, because if you do it, then you will get one of these options. So whenever such option is there, then first we need to find the characteristic equation and find whether the system is stable or not, and then we should use the table. Okay. question is saying that a satellite attitude control system as shown below has a plant with transfer function gs is equal to 1 plus s 1 by s square cascaded with a compensator cs is equal to k s plus alpha s plus 4 k and alpha are positive real constant. Okay, so in order for the closed loop system to have pole at minus 1 plus minus j root 3, the value of alpha must be. So here we need to just find characteristic equation two times. First using this block diagram and applying 1 plus gshs equal to 0, and second using these poles and then equate them. Okay, so here it is k s plus alpha s by 4, it is 1 by s square, so complete gs will be k s plus alpha s square s plus 4. Okay, so characteristic equation which is 1 plus gsh is equal to 0 will be 1 plus this thing equal to 0. So when I take this as denominator s square s plus 4, then it will be s square s plus 4 plus k s plus alpha, and then this denominator will go to this side and become 0. So this is the characteristic equation. So it will be s cube plus 4s square plus ks plus k alpha equal to 0. So this we have made third order characteristic equation. Now we need to make one more using these poles. So since minus 1 plus j root 3 and minus 1 minus j root 3 are the poles, so factors will be s minus minus 1 plus j root 3 and s minus minus 1 minus j root 3. So from these two we can make a second order equation. So this will be s into s is s square, s into this complex number will be s plus j root 3s. Okay, then s into this complex number will be s minus j root 3 s, and then when I multiply these two complex numbers, then you know that a plus ib into a minus ib is a square plus b square, because I square is minus 1 or j square is minus 1. So this thing will give us 1 square plus root 3 square, which is 4. These two will cut. So finally I will left with s square plus 2s plus 4. But since we need a third order equation to compare the two, so what we will do is we will assume a third order, we will assume another pole at s is equal to minus a, because we will not assume s is equal to plus a because we need stable system. Okay, we assume the system is stable, so it will s plus a will be also a factor. So now I introduce s plus a with this thing, so I will now multiply them, so it will give me s cube plus 2as plus 4s. Okay, first I multiply with s, so s square plus 2s square plus 4s, then as square plus 2as plus 4a equal to 0. Now s square के coefficient 2 plus a, s के 4 plus 2a, and this is 4a. So now I have two equations, just I have to compare them. So you can see that 2 plus a is equal to 4. Okay, 2 plus a is equal to 4, so a is equal to 2, and 4 plus 2a is equal to k, and a is already 2, so 4 plus 4 8 is equal, so k is equal to 8. Now last is 4a is equal to k alpha, so k is 8, a is equal to 2, so alpha is what? Alpha is 1. Okay, so finally the value of alpha is 1. Okay. So in all such question, some information is given in terms of equation, some in terms of block diagram, and we need to equate them. Okay. Another question is on Routh-Hurwitz criteria, concept of relative stability. It is saying that consider a negative feedback control system with forward path gain gs equal to k upon s plus 1 s plus 2 s plus 3 as shown below. So this is the impulse response of the closed loop system decay faster than e की power minus t is. So it's asking about the values of k for which the impulse response of this closed loop system will decay faster than e की power minus t. Okay. So decaying faster than e की power minus 2t, what does that mean? So let's try to understand it little bit. Suppose xt is e की power minus t ut, then its graph will be like that, and if e की power minus 2t ut, then graph will be like that. So you can clearly see that at t is equal to 1, its value is 0.36. For here the 0.31 value is 0.315 at t is equal to 1. So clearly this graph is decaying faster. Now when I take Laplace of this, it is s1 upon s plus 1, but it is 1 upon s plus 2. Okay. So here the pole is at s is equal to minus 1. Here the pole is at s is equal to minus 2. So you can clearly see that more the pole is closer to j omega axis in s domain, slower is the decay in time domain, and farther the pole from j omega axis in s plane, faster is the decay in time domain. Okay, so this is the dominant pole concept. Thus pole which are closer to j omega axis in the left half of plane, they decay relatively slower, which implies that poles far away from j omega axis lead to faster decay. Okay, so now we know decaying faster in time domains means pole farther away from j omega axis. Okay, so here he is saying about impulse response of closed loop system decaying faster than e to the power minus t. So in time domain, value of k for which impulse response of closed loop system decay faster than e to the power minus t means values of k for which the poles of hs is on the left side of s equal to minus 1. Okay, where hs is ys upon rs is nothing but gs upon 1 plus gs. Okay, ys upon rs is hs, which is gs upon 1 plus gs. So this is gs 1 plus gs. So when I solve it, I get this thing. Okay, or directly I can write it characteristic equation is 1 plus gs hs. Hs is 1 here, so I get this characteristic equation, which is s plus 1, s plus 2, s plus 3 plus k. So this is the denominator polynomial of this thing, and this is the characteristic equation. Okay, but we need to find the poles. We need to find a value of k for which all poles lie to the left of this thing. So we will do a relative stability. We will use the concept of Rautherwitz. So what we'll do, we'll put s is equal to z minus 1. Since we need this thing is minus 1, so we'll just put s equal to z minus 1. Okay, this. So when converted into z, so dz will be s plus 1 is equal to z. Okay, s plus 1 is z, because this is z minus 1 plus 1, so z, then s is equal to z minus 1 plus 2, so z, this is z plus 1, then this is z plus 2, and then this is k. So finally it becomes an equation in z cube plus 3z square plus 2z plus k. So now when I will solve it and apply Rautherwitz on it, then what will happen is I will find the poles which are to the left of this thing. Okay, so you shifted the origin from s equal to 0 to s equal to minus 1 using this simple transformation. So z cube z square z1 z0, this is 1 2 and then 3k. So when I multiply it, so it will be 6 minus k by 3, and then this will be k. So for all the poles to be on left side of this, we need first column should have all terms positive, no sign changes. So this means 6 minus 3 by k greater than 0, so which means 6 minus k greater than 0. So this means 6 greater than k or k less than 6, and this thing should also be positive. So when I compare them, I get k value between 0 to 6. So best option out of 4 is k between 1 to 5. Okay, so it's a relative stability problem, and the main thing is decaying faster than e raised to power minus t means the poles of hs should lie to the left of s equal to minus 1, and therefore we need to make a simple transformation that z is equal to s minus 1 in the original characteristic equation and apply the Rautherwitz criteria. Okay, so that was the main thing. Last question is on state space analysis. It's an easy question, but actually little time consuming. It is saying that consider a system as represented in state space like this: dx by dt is equal to 0 minus 2 1 3 x plus 1 0 r, y is equal to 2 minus 5 x, and d 0. So which of the state representation given below has the same transfer function as that of s? So first we need to find this transfer function of this thing, and then we need to, it look like we need to find transfer function 4 times and 1 time here, so 5 times, but actually these two are diagonal canonical form and this is controllable canonical form. So 3 can be easily found directly using shortcut, but at least this one we need to find. Okay, and first we need to find this one and then we will try to convert it into CCF and ECE form and we'll find the which option is matching. Okay, so state model is given to us. X dot is equal to this thing which is ax plus bu. Here they have written u as r, this is the input, and y is equal to cx plus du, d part is 0 here. So we know the method transfer function is c si minus a inverse b plus d is 0, and si minus a is nothing but s2 minus 1 s plus 3 because si is s0 0 s, and then minus a matrix which is a matrix is what, it is 0 minus 2 1 3. Okay, so this when I do, then I get this thing. Now I take its inverse using this is ABCD, so this is 1 upon AD minus BC, and we interchange them and we put minus sign here. So finally I get 1 upon s square plus 3s plus 2 s plus 3 minus 2 plus 1 5. Okay, now when I multiplied by C matrix which is 2 minus 5 and B matrix, so first I multiply these two. Okay, so this is a 2 cross 1, this is 2 cross 2, so final answer will be 2 cross 1. So s plus 3 into 1 plus minus 2 times 0 and 1 into 1 plus s into 0, so it will be s plus 3 and 1. Okay, and now I multiply these two. So when I multiply these two, so this will be, it is 1 into 1, it is 2 into 1, so it is 1 into 2 and it is 2 into 1, so final answer will be in terms of 1 into 1. So it's basically 2 into s plus 3 plus minus 5 into 1, so this is 2s plus 6 minus 5. Okay, so this is basically 2s plus 1 s square plus 3s plus 2. So this is the transfer function. Now we just need to convert it into first CCF form because this answer is in CCF form. So how do we write it in CCF form? We write in this fashion and write a matrix using this. So this part is always 0 1 and this here is we use minus sign, so minus 2 minus 3. Okay, and in B we always write first as 0 and then second entry is this coefficient which we taken out. So here I have taken out 1, or you can also take out 2 common, then it will be 1 plus half. So but this is not in any option, so I will not use it here. So 0 and then this one, then C will be this thing, numerator part 1 2, so 1 2. So this is exactly matching as in option A, so option A is correct. I have written this transfer function in CCF form. Now we need to check which one of them is the correct diagonal form, so I will take partial fraction of the original transfer function, okay, that you have derived. So this will be, I put s is equal to minus 1 into this thing, so this will be minus 2 plus 1, so minus 2 plus 1 is minus 1 and this will be minus 1 plus 2 is 1, so this is minus 1, and I put s is equal to minus 2 in this remaining thing, so minus 2 plus 1 is minus 1 and this will be minus 4 plus 1, so minus 3 upon minus 1, so it is plus 3. So now to write the DCA form, we just take this numerator minus 1 and minus 1 and minus 2, these poles, and this part as it is as minus 1 and 3, and y is 1 1. Okay, because minus 1 into 1 and 3 into 1. Okay, that's how we write it. So you can clearly see this in option number C. Okay, minus 1 into 1 and 3 into 1, these are the coefficient, so these are coming here. Okay, 3 into 1 is 3 and minus 1 into minus 1 is 1, so these products need to be checked out. So C is matching, D cannot be correct diagonal form and B cannot be correct CCA form. So basically he is asking about first he is asking about whether you know how to find the transfer function or not, and then he is asking about whether you can convert the transfer function into CCF and DCF form. So it was little bit lengthy question and it should be done in the last, otherwise it will take at least 5 minutes. Okay, so you can directly convert them into this final option also. Like this part is not in answer because 1 into 1 and 1 into 2, so this will be 1 and this will be 2, and these factors are s plus 1 s plus 2. So now when I multiply them, so you can see that I am getting 3s plus 4 upon s square plus 3s plus 2, but actually answer was 2s plus 1. So that we are getting only in above option, not in this part. Okay, so that's how we have to solve it. Okay, so these were all the 5 questions. Thank you.